going? I'm Alex Rickabaugh. I'm a software engineer at Google in California. Just happened to be visiting Poznan for the week and was invited to come and talk to you guys about Angular. So thank you very much for the organizers for having me. I've been at Google for about 8 years, and for the last 3 years I've worked on the Angular core team. I'm actually surprised, like I talk to people at Angular conferences and not everyone knows that Angular is actually a Google-sponsored project. It originated there. We still have a team of maybe 20 to 30 people working on the framework, and we use it a lot internally. How many people here have used Angular 1.x, like the AngularJS version? Awesome, okay. How many Angular 2 or above, like the new version? Fantastic, okay. So I'm going to talk a little bit about a project that I'm working on that we're doing on the Angular team called Ivy. Ivy is our next generation kind of rendering engine. And it'll be a little Angular specific, but we'll also talk about some techniques in JavaScript that apply to a lot of different applications. And so what I mostly work on the Angular team is our compiler. If you haven't used Angular, essentially you write HTML in our syntax, our Angular template syntax, and you run a compiler that's based on TypeScript that transforms that template into code that runs in the browser and actually renders your UI. So Angular is kind of one of those model, view, whatever frameworks. So yeah, I'm going to talk about Angular Ivy. So as I said, Ivy is our new rendering engine. It replaces something called the View engine, which was debuted in Angular 4. But you can also think of it as an architectural replacement for how Angular works internally. And what it does is it brings Angular up to date with the state of the art of tooling in the JavaScript ecosystem. So when we first started kind of going from Angular 1.5 at the time, I think, to the new version, the ES6 ecosystem in JavaScript was really kind of just getting started. There were a lot of different tools, they had different capabilities, but nobody really knew like what's the best practice for shipping code to the browser, what's the best practice for shipping code on NPM. And the tools that did exist kind of solved half of the problems, but didn't really work well with the tools that solved the other half. And so we kind of were designing this thing in the blind. Like we didn't actually understand what the final solution would look like. But fast forward a few years, JavaScript has come a long way. We have tools like Webpack, we have tools like Rollup. Uglify has really good support for modern features like tree shaking. And we can actually kind of take a step back and rethink our design and really make the framework in a way where it gets the best, gets the benefits of the best tooling that's out there. And two of those features that I wanted to talk to you about are tree shaking and this concept of monomorphism. And so we'll get into what those mean. So tree shaking is simply the practice of removing code from the application that you ship that doesn't actually get executed. And this can happen, this can end up in there for a lot of ways. First of all, like in your code, you could simply forget to delete things. Or maybe you compile your application in a production mode and your debugging code doesn't get called. You really don't want to pay the cost of shipping those bytes to the browser. But also, if you use a library, for example, Angular has our Material UI library that you can download. And it has, 24 components in it. And some of them are fairly simple, like the button. Some of them are really complicated, like a data table. And if you only use a handful of those, you really don't want to pay the cost of shipping the rest of them to the browser. And so tree shaking is the feature of bundlers and kind of the compilation pipeline that goes from your application code to the browser that takes care of this for you. And its job is to look at what actually gets used, what code actually gets executed at the runtime, and include only that, and strip out everything else. And so some of our changes in Angular from version 2 to version 4 have been based around making your applications more tree shakeable, making it easier for these tools to recognize that components or classes or services are not used, and for the tool to strip them out. But what we noticed was that was working really well for applications, but the Angular framework itself was not being tree shaken very well. And that's because Angular was kind of written as this giant if statement. Like if your component has this feature included, then here's the code to actually make that work. And if your component uses this other feature, then here's the code to make that work. And it turns out the tree shaker can't know ahead of time if that if statement is going to be true or false. So solving this problem really required radically rethinking how Angular is architected under the hood. And we'll get into that. Monomorphism, on the other hand, is a performance technique. So here we have some example code. I just have two objects here on the left that we define, component and directive. These are two types of objects you can create in Angular. And we define both of them with a selector field. But the component has this is a component property, which we set to true. And the directive has this is a directive property, which we set to true. And this looks like nice and innocent code. Like, it's a fairly simple design. And what we're doing is we're calling this update function here on the right, and we're passing in the component, and then we call update again, and we pass in the selector. And the problem is that in the JavaScript engine that's actually executing this code in the browser, these two objects have a different shape. They have a different set of keys. And so the JavaScript engine, when it compiles this update function just in time to machine code, it doesn't actually know what shape of object is going to come through. And so it defaults to a slower mode of execution where it inserts a bunch of guards to make sure, I actually have to go and read this property type.selector here. This lookup has to happen by consulting a hash table with a named selector, figuring out what the, where on this object that's coming in this property is stored in memory and accessing it. And this can be up to 100 times slower than something called a monomorphic property access. And what that is we made sure that our object coming in has the same shape. Both of them have both a selector and a type key. And when you do that, the JavaScript engine is able to recognize that this update function only gets called with objects that have a selector and a type key. And it can do a very fast property access where it says, oh, the selector is stored at the first index, the first part of memory for this object, no matter what object comes through. And it turns out that is 100 times faster. And so this is something that we've kind of learned through the years building Angular. And when we were embarked on this Ivy project, we decided to take this to heart and really design the framework around this idea that our fundamental data structures should always be monomorphic. They should always have the exact same shape. And it turns out you get a really incredible speed up doing this. So a little bit of history. Angular started with a rendering engine you can roughly call the ng factory approach, where you wrote a component, which was the logic for your UI, and you wrote a template, which is HTML that described the view. And Angular would compile the HTML, turn it into a class called the component factory, and it would compile out literal document create element instructions. And we thought, this is going to be amazing. This is going to be incredibly fast. So, instead of having all this overhead of a framework which has to interpret the template, you would literally, at build time, produce the DOM instructions to create the view, and it was going to be incredible. And it was, except it turns out that generates a lot of code. Most applications have really complicated views, lots of them, and it got kind of bulky. So then we went, with Angular 4, we introduced this thing called the view engine, which went a different direction. We said, okay, instead of generating literal instructions, we're going to generate a data structure that describes the UI. There's an element here, it has a click listener attached, it has a text binding. So these data structures can be nice and small, just little JSON objects. And then we'll have a part of the runtime called the view engine, which interprets them and actually does the document create element. And that solved the size problem. Templates got much smaller. But the problem is that became very megamorphic. These data structures were always different shaped. And so the runtime was never able to execute in the fastest mode that the JavaScript engine can do. Because the runtime always had to have these special type guards that says, okay, how do I access this property? What type is coming in? I have to do the lookup the slow way. And so Ivy kind of unifies both of these approaches. So our mental model is that in Ivy, when you write Angular decorators, which are at component annotations that you put on classes to say, to tell Angular, this is a component, this is a directive, this is a service, this is a module, etc. They get compiled down to static fields. So this is what that looks like in code. So on the left is a standard Angular component definition. This component has a selector of app component. That's just the HTML tag name that's going to be used when you create an instance of this thing. And it has a template, which is a paragraph tag with hello world. And when you run our new Ivy compiler, what you get is the code on the right, where this app component class has an ng component def static field, and it calls this define component function. And the really nice property here is that the define component function makes sure every component definition that comes back has the same shape. It's always going to have the same fields regardless of what you put in the decorator. And that makes sure that Angular's runtime can be entirely monomorphic. So we did this for all of our decorators now. And the nice thing is this actually makes testing really convenient, because the decorator itself will actually create the static field when you're running in what's called Angular's JIT mode, which is you're not using our compiler as part of your build pipeline, you're letting the browser do the work of compiling these things. And so you can write a test, and previously you had to go through all these machinations to tell Angular to compile the class, hook up metadata to make sure you can import things. Now you can actually just directly invoke the decorator and it works. And when you're running this as part of your build pipeline, you run our compiler, it just does the exact same thing that was happening in the browser at runtime. And what happens is, instead of turning that template into document create element instructions, and instead of turning it into a data structure, which is very concisely describes what the template was supposed to do, but is very megamorphic to read, we turn the template into calls to these new, what are called Angular view instructions. So we kind of developed an instruction set for the web that's like element start, element end, text binding, etc. And so that first if block here is actually creating this component. So it calls element start, it tells Angular, okay, we want to create a new element, it has a certain style, it has a span inside of it, that has a text, literal text inside of it. And the second if block here is actually our change detection block. So every time you interact with the application, Angular runs this process called change detection. We try to reconcile what you have in your model with what should be shown in the view. And so this is executing the bind instruction, checking this variable in our class that says show hello, and if that's true, then the hello world should show up. And the nice thing about these instructions is, if you don't use them, if you don't write a component which actually exercises some feature of Angular, the tree shaker can remove them. So the Angular framework can just completely fall away if you don't use it. And this allows us to get our kind of basic applications down much smaller. The other thing is you can actually load those instructions later in the browser if you want to. So if your home page doesn't use the instruction, you can delay loading of that code. They're also nicely monomorphic, and a really cool feature is that they're debuggable. So I want to show you what this actually looks like in practice. So this should work here. Drop over to my editor. Can everybody read that? Okay, is this font size good? So this is a very simple to-do application in Angular. We have some to-do class, they have titles, we have a store for them. This is kind of not really important for the demo. We have this nice complicated view that's going to show all the to-dos in kind of an array. And what I'm going to do is go ahead and build this. I already have it built, so it's nice and fast with Ivy. Let's full screen this guy. So we get this nice to-do application. I can interact with it. Chill.js. Cross things off. And if we go and look at the generated code, let's actually look at the non-minified version. Best view of this. actually see that this component got us component def, and that template that we wrote was turned into this function which actually calls instructions to create this view. And the really nice thing about this, which wasn't really possible in Angular to this date, is I can put breakpoints in here. So I can say, I want to know exactly when this to-dos text at the top is rendered. Maybe it's not showing up properly, maybe it's showing up in the wrong place, and I want to understand why. So if I just add a breakpoint at this text instruction that actually adds that text, then when I refresh it, we actually ended up stopped at that point in the execution of rendering. And if I step over that, it got added to the DOM. And as I step down here, we see kind of the UI starts to render piece by piece. And the really cool thing is with source maps, we can actually map this template function back to your HTML. So imagine setting a breakpoint in your HTML template. Like, I want to stop when this particular bit of UI is rendered. The browser will do that just fine. So that is the demo I had for you. And yeah, I wanted to take a few minutes just to talk to you guys and see if you had any questions, interesting stories about using Angular or other frameworks. Like, feel free. Yeah. Cool.
So maybe,
yes,
you showed us how to easier debug a bundle, but because this is another approach in Angular framework, do you have any comparison in terms of performance in the browser to the previous version? It would be nice to...
Yeah, I don't have any numbers in terms of performance to show you. Our benchmarks, we run them on Google infrastructure, which has you have dedicated machines that have known performance characteristics that don't vary over time, unlike this laptop, which, depending on how hot it is, they can run fast or slow. I can show you some size numbers, which are pretty cool. So let's build our SPR. So we're going to build a compressed version of this bundle that's optimized for shipping to production. And this is a Hello World application, which just has the text Hello World on the screen. And so this ends up at about 3.3 kilobytes, which compared to Angular View Engine, I think that would be around 50, maybe 35 with really good compression. So tree shaking really kind of shows up here. Like, we can remove major parts of the framework. Angular supports dependency injection. Dependency injection is done with an instruction. If you don't use it, if you don't have DI in your application and you want to create services manually, you don't pay the cost of including any of the mechanisms in Angular to make that work. If you don't use subtemplates, like you don't have ngIf or ng4 to loop over things or to show or hide bits of UI, those fall away. Yeah, no problem. Any other questions?
So yeah. You said about this instruction set being created for Angular, and there was recently rewrite of React, React 16, and they re-implemented threads, basically.
The fibers, yeah.
Yeah, exactly. And can you see any other patterns repeating from lower levels of abstraction, management of system processes or something like this? Do you see anything like this implemented inside of Angular?
We're definitely very excited about one of the cool things about the instruction set is that by necessity these APIs have to be public, because you're going to build libraries, you're going to ship them to NPM. They're going to have to continue to work in Angular from release to release. And so people can build tools that have other ways of compiling templates that generate the instruction set. And so, yeah, you could imagine some interesting integrations there. We are thinking about higher order components, which is something that React does pretty well. The Ivy, we haven't done any implementation there, but the Ivy model should make that more achievable if people want to try that. As far as other kind of corollaries with lower level system APIs, none that I can think of off the top of my head. But feel free to tweet me and I can get back to you.
Okay, thanks.
So those instructions are created like step by step to every change, or it's like you're trying to have a set that is most optimal, the best set of changes that will do the job on the computer.
Yes, so
doing all of them, or just doing only those that need to be done to get the right.
there are a number of instructions, and right now they're very much in flux as we develop Ivy and kind of learn which patterns tend to work well. The goal when we ship a final version, which is whenever it's done, honestly, it's an ongoing project. Our goal is to have a minimal set of instructions that cover and allow us to reproduce Angular's behavior as it exists today. Because one of the goals of Ivy is we can't actually break existing code that's out there.
Will be close to like this particular component, or is it going to be like trying to calculate the best changes in the set of components, for example, a set of components?
Oh, so I should talk about that. Yes, thank you. One of our other principles in Ivy is called locality. And to understand that, you have to kind of have a little context of how Angular used to work before. When you would build your Angular application, it would go out and analyze your code, all of the libraries that you were using, all of the libraries that they depended on, and it would create a full kind of data structure of everything Angular in your entire application. Your components, material design components, anything you download in your charting libraries, etc. And it would generate code for that. So it would do kind of global analysis of your entire app before it can compile. And it turns out that's slow. Especially when you're trying to do this, like I want to be able to edit a file and save it and refresh in my browser and see it update in under 2 seconds. It's really hard to do things kind of over the entire code base. So Ivy adopts this principle called locality, which is the only things that affect the component compilation are in the component decorator. The only things that affect the service compilation are in the services decorator. And so the instructions generated for a component are unique to that component's template. They don't take into account any other part of the application. Our compiler has some sort of optimizations there for tree shaking to be able to say, oh, this component is actually not going to use these things. We shouldn't reference them. But in general, each component is compiled as a unit.
So if you make your instruction set public, are you thinking of or imagine writing another interpreter for the instruction set so that it wouldn't render to the DOM, but something
that is a really cool idea.
Weird.
So we have server-side rendering support, but it turns out that even if you are DOM independent, like Angular version 4 or so was DOM independent, and that you could replace this thing called the renderer with any implementation you wanted. It turns out users call DOM instructions anyway all throughout their application. And so our server-side rendering now works by emulating the DOM using the Domino library. So yes, there are frameworks that are like NativeScript, which kind of interpret Angular templates in a different way, where I could actually see someone doing something like that. So we don't have any plans to do it, but it would be really cool to see a project that does.
Okay, thanks.
And the same, it would be really cool to see a project that took another kind of template syntax and compiled it down to our instruction set. We're really excited about the potential for people to kind of build on top of this. Anyone else?
So maybe another one for me.
Yeah.
For what kind of project would you recommend Angular? Because lately Google have shipped some new version of their apps, and Angular wasn't the tool they used. So why is that?
Yes. Google teams internally are free to kind of pick the technologies that they like to use. A lot of them do use Angular. In particular, a lot of our internal kind of line of business applications built with it. Google Shopping Express, I think, is one project which uses Angular externally. probably think of a few others, but yeah, in general, we see our usage kind of growing both inside and outside.
Yeah, because with this new interpreter, when the model size might be that small, maybe
Yeah.
it's
Absolutely, yeah.
spread it. Okay, thank you.
Cool. Thank you guys very much for having me.